Up to this point in the class, we've described the derivation of both the least squares estimators for one variable regression and multiplying matrices together for one variable regression. And that has enabled us to describe potentially how we could compute multiple slopes if we had more than one variable in the regression. And that's important because if you take a look at what you've done up to this point in statistics, we've said, hey, you can include multiple variables in the regression. We just haven't had any description as to how the numbers that are spit out of your Excel output or your R output, how those are derived. So the previous videos provide us some guidance as to what that would look like. In the previous video, we described the standard error associated with the slope. And we had said that this was a description of how far the data are away from the line that we've created with the given estimated slope. We use the standard error to test the hypothesis that the slope of the line is equal to 0. And so what we did is we went back and we calculated a sum of squared residuals by multiplying a transpose matrix of the errors times the error matrix itself. That generated us one parameter, the regression variance, which we then evaluated against X transpose X inverse. And we use that to construct a measure of the variance of the slope for our given X. And we use that to test the hypothesis. And so what this method does is it essentially fuses together all the variation from the line into one parameter, the regression variance, which is fine if there's no pattern to how the points are dispersed around the line. But you might think of a line where the line fits very well for part of the domain for X, but does not fit well for other parts of the domain of X. So, think of estimating the relationship between how fast it takes to run a mile and age. You may have quite a bit of precision around college age students, but then it may vary quite wildly among older people. Nonetheless, we could fit a line through the data and potentially test a hypothesis about the slope of the line, but there's a lot more variation around the line for older ages than younger ages. So we might think that the line is a really practical exercise for those in a certain age group, but is impractical in another age group. So what we often like to do in these cases is instead of just splitting the sample by certain subvalues of X, which is pretty arbitrary, maybe we can fix the standard errors in some way to account for the fact that some data are further away from the line than other data. So the regression variance that we estimated isn't constant for all X. So the standard error tells us how accurate it is to interpret our slope as being demonstrative of relationships between X and Y. And you note here on this slide, I have X as a vector. So we're thinking of X as including X1, X2, X3, etc. I'm always able to estimate a slope. So if I do X transpose X inverse times X transpose Y, I can get as many slopes as I have X variables, as long as I don't run out of degrees of freedom, and I'm fine. Okay, however, the standard error and test statistic contextualize how the estimated slope that we have relates to no relationship whatsoever of 0. So if the points are far away from the line, we don't think the line fits well. However, sometimes, as we described previously, some of the points are close, others are far away, and so in these instances, we tend to get test statistics that indicate a relationship, but it's not quite as clear-cut as that. And so what we try to do is fix this problem where some points are close to the line for a certain domain of x, and then for other parts of the number line, they're far away. And so we're going to look at two measures. One is what's called heteroskedasticity-consistent standard errors, and the other is what's called cluster robust standard errors. And so for the heteroskedasticity-consistent standard errors, I will show you how they are constructed, although we will not construct them ourselves. So heteroskedasticity, what is it? Well, it's a very long word, but what it means is that the standard errors differ depending on values of x. So the regression variance, how the points are dispersed around the line, is not constant anymore. So it is inappropriate to treat each data point as being the same distance away and just multiplying the transpose matrix times the error vector. That's inappropriate anymore. What we want to do instead is potentially allow the error in x to be related in some way. And so what this will do is it will increase the amount of variation that we allow the points to have around the line by not averaging that variation across all the points. So what we do here is we just allow x and the error term to be related to each other because very clearly they are related to each other. So the line fits really well for some x but not for other x. That means that there's a relationship between the size of the mix and the value of x. And so we just allow for this with what are called heteroskedasticity-consistent standard errors. So really what it boils down to is we inflate our standard errors by n over n minus k rather than just dividing by n minus k. Now we account for the amount of data that we have. And so we are increasing the standard errors. Usually in this instance, it usually reduces the size of the test statistic, makes us less likely to reject the null. So this is something that we have to try to do to correct for the possibility that x and the error term are related to each other. Previously, what we did to construct the standard errors, let me just show you here on these previous slides. I'll open them up. Previously, what we did to calculate the standard error, you can see we multiplied the regression variance times x transpose x inverse, and we calculated the regression variance by just multiplying the errors together, making a sum of squared errors, and dividing by n minus k. Now what we do is we say, well, we still want to find the variance of beta 1x, but we're not going to just treat the errors as being this constant. What we do instead is it essentially we regress the x's on the errors here. Okay, and that's what's going on here. So this is like a regression of x on the error term. So it uncovers the relationship, and then we go ahead and we estimate the standard errors afterwards. So this is a lot of work. R will do this for us. Excel will not do this for us. So this is why we start to think about using other programs, is because we want to fix our standard errors. This diagonal matrix is the squared errors themselves. So the squared errors come directly from the line that we fit. This is the line we fit through the data. This is the value of x. You plug it into the line, you get the expected value of y given x, you get an error. Those squared errors are put onto their own matrix. This is called a diagonal matrix, and we just square them out. Okay. And we multiply left to right to find the new standard errors. You can see that this is just a ton of work. You are not required to do this, but I do want to show you how the errors that you get in R are constructed. So you can see a comparison of our previous standard errors to the ones that we have on this slide. You compare these two to each other. You can see that our standard errors went up a little bit for some values of x here. And we just take the square root of this and we have a new test statistic compared to the old test statistic that we had previously. So basically the heteroskedasticity-consistent standard errors are a tool to correct for the possibility that x and the error term are related to each other. So this is a lot of technical detail on these slides, and I don't want us to get bogged down onto it. Really what I want us to think conceptually is that in order to allow for x and the error term to be related to each other, which they almost certainly can be in real life, we do occasionally have to allow for there to be a relationship between x and the error term, and we allow for it here by regressing the x's on the squared error terms. We don't do that here. Okay, so the error terms are dealt with independently of x. They're fused into one parameter, and we take that parameter and multiply it by the x transpose x inverse matrix. We don't do that here. We don't do that here. We allow for x to be related to the error terms. And that is what all of these slides are doing. And you can just see I have multiplied a huge number of matrices together in order to calculate the standard error, but you can verify for yourself. There are other problems that we may run into when we estimate a regression model. And one problem is that we may not have concern that x and the error term are related, but what we may have concern with is that, say, different groups within our data set have errors that are related to each other. So sort of the classic example is classroom identity when trying to estimate the impact of education on any long-term outcome. It may be the case that students who are in the same classroom have outcomes that are correlated with each other because of this stuff. So think of that category as being a potential x variable in and of itself, but also think of the dispersion associated with that category as being related to other observations in that category. And so you could think of accounting for the category directly, but you may also want to understand that even after we estimate the relationship of being in the classroom on those outcomes, the observations within that category might still be dispersed more similarly than other points at large. And so what we do is we just cluster. This is what's called clustering, and we allow for the data within a cluster to be related to the error term, but then data outside of the cluster are not related to that particular error term. So it's kind of like, instead of allowing for every possible value of x to be related to the error term, we only allow for a subset of x that belong to a particular category to be related to the error term. So we're only interested in within category dispersion for a large group of x. And R can do this for us directly, so this is not, again, something that we have to worry about. We will look into this later on. Adjusting the standard errors is no fun, so this is a slog to listen to. but is a necessary part of regression analysis. So just kind of a comment that I would have about this is these are the first sets of things that when you're doing applied work, people tend to look after. Did they do this or not? Did they account for heteroskedasticity? Later on when we talk about time series regression, did they account for potential autocorrelation between the error terms? The errors are correlated across time. Did they account for this grouping problem? And if you didn't, then when you tell me that there's a statistically significant relationship between X and Y, I have a hard time believing you because I know that there's some potential problems with your domain of X. So we just have to try to fix it. We're going to look at some methods to fix it within R, but this is something that we worry about when we're doing applied work. Now, what's more fun to do is debate what to include in a regression model. So fixing the standard errors is kind of a necessary evil, but now we get to kind of explore some things that might affect Y, which is presumably what we care about. And the first thing I want to point out is what's called a limited dependent variable. So categorical data, whether or not you belong to a class, for example, or your race, or your religious beliefs, or your gender, these things can be included in a regression model. Now, some of these things are not especially interesting to predict, so we wouldn't think that there are a lot of variables out there that we're going to be collecting necessarily that could predict your gender. And we wouldn't think that there are a lot of variables out there necessarily that we could collect that would predict your race, but we might think that there are variables out there that could predict whether or not you make a decision, where 1, you make the decision, 0, you choose not to. So we will often take up to look for models where we estimate the probability of completing a task or the probability of doing something. So you're making an economic choice, you've done it, that's a 1, you didn't do it, that's a 0. What's the probability that we change from 0 to 1? This is what's called a linear probability model. Now we can estimate that using the techniques that we've already learned using ordinary least squares. Okay? We can do just fine there. In econometrics, if you go on to take that class, you're going to learn some other methods, logistic regression and probit models that give us a little bit more wiggle room in that we're restricting the probability to be between 0 and 1, whereas with OLS, that's not necessarily the case. Now, oftentimes in real life, people will just use OLS to estimate these 0-1 relationships, but in principle, you may want to explore something else, like a logit model, logistic regression, or a probit model. So Y could be a 0-1 choice. Or we could have Y be some type of numeric answer that's explained by these limited dependent variables. So you think about maybe the state that you're from and that influencing some educational outcome of interest. Well, I can have a variable that takes the value 0 if you do not belong to that state, and 1 if you do belong to that state, and that is a limited variable. So let's say I have a bunch of categories. Let's say I want to include all the states. I can do what's called a fixed effects model, where I include a variable for all possible categories. So if I have 50 states, I include 49 variables in my model, and if you're not in the first 49, the 0 is for the 50th state. Okay, so we can do this. This is commonly done. So we often want to include these fixed effects in our model just to ensure that the relationship that we've estimated between X and Y isn't something that we can just chalk up to be, well, in this particular county, they have a lot of X. In other places, they don't. So it's not really X that's impacting Y. It's just that you're in this county. So we often do these fixed effects to eliminate the possibility of group-specific variation or geographic-specific variation as being the explanation for why X impacts Y. And this is what's called a fixed effects model. We can also include polynomials for x in an equation. So take a look at this relationship. I'm trying to explain why. I include x1, I also include x1 squared. So if you think about the relationship between education and experience, your income goes up fairly quickly at younger years of your career, but then as you begin to get older, it goes up less quickly. So there's this nonlinearity of the relationship between experience and, say, salary. This is something that we can capture with both beta 1 and beta 2. So maybe beta 1 is positive, but beta 2 is negative, something like this. We can also include what are called interaction terms. So variables may independently provide information related to the conditional mean of y. However, they may also have meaning together. So think of the relationship between race, gender, and income. This is what was used in Hanson's textbook. So there's a relationship between gender and income. There's a relationship between race and income. There is also an interaction between race and gender and income. So if you think of the effect of being a black woman on your impact on your income, there's an impact of being black. There's an impact of being a woman, but there's also a separate potential impact of being a black woman. And that is something that, as we try to address things like inequality, as we try to think about how to improve um, outcomes that we're concerned with in society, we want to estimate those separate effects so that we can begin to understand the magnitude of a problem. So if I chalk everything up to just being a particular race or just being of a particular gender, I may be systematically ignoring some important biases that are going on for people that are both of a particular gender and of a particular race. And I don't want to do that, but I will do that if I don't include this interaction term. So what I can do is I can have a term for x1, I can have a term for x2, and then I can have a term for x1 times x2. So if I have a 1 being female, 0 if not, 1 being black, 0 if not, then if I have a 1 for both categories, I have a 1 times 1 for x1 and x2. So beta 3 is capturing that estimate. Um, and that is something that I think we need to consider including more in regressions are these interaction terms where we try to see whether or not there's a separate effect of being in one group versus another group. The last thing I want to point out is what are called log specifications. So when we use log in economics, we tend to use it incorrectly. We actually mean the natural log ln. So ln of 1 is 0. ln of 0 is minus infinity, which is related to the function e to the x, such that e to the 0 is 1 and e to the minus infinity is 0. And because log of 0 is minus infinity, sometimes we'll just add 1 to make it start at 0. So what we do with these log specifications is we use it to flatten out distributions of things like income, which have very, very large right tails, and they have a lot of probability around the leftmost censored value of 0. We try to use the log specification to turn this into something more normal, looks more like a normal distribution. So we'll often estimate what are called log-log specifications, where the log value of y is equal to beta 0 plus beta 1 log of x1 plus beta 2 times x2, etc. Now, we can interpret the beta 1 coefficient here as a 1 unit change in log of x1 is a beta 1% change in y. We can also interpret x2 in terms of a beta 2 in terms of a percent change. We just have to raise e to the beta 2 power and multiply it times however big the change in x that we have is. So if we go to 2 to 3, then the change in x2 is 1. But the idea behind these log-log specifications is instead of trying to estimate like what a $1 change in income will do to Y, we may be better off measuring like what a percentage change in income will do to Y. So we may be better off converting from units to percentages, and the log-log specification is where we do it. So we tend to do this for wages, population, salaries, firm sales, anything where we have large integer values. We tend to start to want to think of things in percentages rather than one unit change, because one unit change can be really small. So this is kind of a laundry list of things that we can do. Over the next 2 weeks, as we finish up dealing with cross-sectional data, we're actually going to try these things. We're going to use real data to estimate these models, interpret them within R, and work from there.